Hi, everyone, and welcome to the pre-lab lecture for the concept of distillation in Chem 231L at Miramar College. I'm going to share my screen so you can see my slides. And then I'm going to take you through the theory and principles behind distillation and the upcoming experiment in the lab. So let's start with the basics of what distillation is. Distillation is the process of vaporizing a liquid, condensing its vapor, and collecting the condensate into another container. What we can see happening here is some sort of heat source is being applied to, in this case, a solution of salt water. And since salt is not volatile, only pure water will evaporate and turn into water vapor. Eventually that vapor will reach a thermometer or some device typically used to measure the temperature. You'll see in the lab that we do, we're going to use a different method for monitoring the temperature. But this would be just an example of a simple thermometer. And you can see it's at 100 degrees Celsius because it's water that is reaching the thermometer and boiling. So once that vapor turns a corner and goes into the condenser, it will cool back into a liquid. And that process is called condensing. And therefore we call it a condenser. The condenser has a jacket around it, sort of a separated glass portion on the outside where we can put in cold water. So that will be put in on the bottom of the condenser. It will go through the jacket, not touching the vapors that are inside the condenser, and then go out the top. And it'll keep this area nice and cool to be able to condense the vapors back into a liquid. And then the condenser and adapter will direct the liquid out into whatever container that you're collecting the condensate in. So I want to review the definition of a boiling point. The boiling point of a liquid is the temperature at which its vapor pressure is equal to the pressure of the gas above it. So recall that there's atmospheric gases, and those are pushing down on liquids, creating an external pressure. And so a liquid must have its own vapor pressure that is equal to the external vapor pressure in order to boil. And typically that would be like 1 atmosphere or 760 millimeters of mercury if it's just normal atmospheric pressure. Okay, moving on to the 4 main types of distillation. There are others, but these are the main ones. We have simple distillation, fractional, vacuum, and steam distillation. And simple distillation corresponds to the picture that you just saw on the last slide. And organic chemists or chemists will use this if they have liquids that are almost pure, or they're solutions where one of the components isn't volatile, like the salt that we saw before, or if the two components have very different boiling points. And it depends on the source. Some sources, like your book, might say 50 degrees or more, and then other sources say it's more successful if the difference in temperature between the two components, or difference in boiling point between the two components, is 100 degrees or more. So you can see that it's really not, as soon as you get a mixture of liquids with anything resembling a boiling point that's even somewhat close, it starts to become an issue for being able to purify one of those liquids, separate it from the other one. In cases where we do have mixtures of miscible liquids, meaning they mix together, they form one solution, then we would typically use a fractional distillation. And that will allow us, hopefully, some better separation of those two liquids that are both volatile or have similar enough boiling point. Vacuum distillation is used for liquids with really high boiling points, like above 150 degrees Celsius. So in those cases, it becomes a little tedious to heat the distillate up past 150 degrees Celsius. And oftentimes compounds start to decompose at temperatures above that. So then it becomes necessary to lower the boiling point. And the way to do that is to use a vacuum. And remember, what a vacuum does is pulling out the gases in the atmosphere, lowering the atmospheric pressure, and therefore the pressure that the vapor above the liquid, also known as the vapor pressure, it doesn't need to be as high in order to achieve boiling. So we don't need to heat the solution as high. But that requires some sophisticated equipment. And so vacuum distillation is the one that we won't be doing this semester. And we will also do a steam distillation. These are typically used for heat sensitive compounds, meaning they have higher boiling points, you heat them a lot, they can decompose, and also they have to be not miscible with water. So that is another criteria. Okay, so if you're looking in your lab manual, what you'll see is that fractional distillation corresponds to part A, simple distillation corresponds to part B of this experiment, and they're both done on the same miscible mixture of liquids. And then part C is the steam distillation of limonene and water. And those are two compounds that are not miscible with one another. To take a look at the structure, you see that part A and part B uses cyclohexane and toluene. And these are both hydrocarbons that are going to have similar intermolecular forces, and therefore it's not too surprising that they are miscible, meaning that they will mix in all proportions. And in part C, the difference is going to be that we're using two immiscible liquids, meaning they don't mix in all proportions. So this is limonene, and we're going to access that by peeling the rind of oranges and water. You can see limonene is also a hydrocarbon, and so it's likely to be much less polar than water. So it's not very surprising with very different intermolecular forces that they're not miscible in one another. Okay, so in order to understand the theory, we need to review some laws, specifically Raoult's law and Dalton's laws. And Raoult's law states that a compound's vapor pressure is lessened when it is part of a solution and is proportional to its molar composition. So if we look over here, I've written this out for cyclohexane, which is one of the two components in the solution that we're going to use of cyclohexane and toluene when we do our fractional and simple distillations. So what it's showing you is that this P naught, which is the vapor pressure of pure cyclohexane, is so the pressure that cyclohexane, the vapor pressure that cyclohexane exerts above the liquid is going to be lessened by the mole fraction, because X stands for the mole fraction of cyclohexane in the mixture. And so if the mole fraction was 1.0, then it would be pure cyclohexane, and then the vapor pressure of cyclohexane would just be equal to the normal vapor pressure of pure cyclohexane. But typically we're talking about a mixture, right? It's going to be mixed with some toluene. So the equation really means that a solution containing, let's say, 80 mole percent of cyclohexane and 20 mole percent of toluene would at equilibrium produce 80% as many molecules of cyclohexane in the gas phase than if cyclohexane were in pure form. So what that means is that when you mix two liquids to form a liquid mixture that's miscible, the vapor pressure from each component of the mixture is lessened compared to its pure form, and it it should be related to its mole fraction in the solution. Okay, moving on to Dalton's law. Dalton's law of partial pressure states that the total pressure in a closed system can be found by addition of the partial pressures of each gaseous component. So what this is stating is that if we have multiple liquids that are going to be forming vapor pressures because they're being heated, that the overall total vapor pressure produced by the solution is going to be that provided by cyclohexane and that provided by toluene in the case of a two-component mixture. So what we really need to do to understand what's happening when you have a miscible multi-component system, like a mixture of cyclohexane and toluene, is combine the two laws. And so what we'll see here is that this particular equation, where the vapor pressure of the solution will then be equal to the individual components' vapor pressures when pure multiplied by their mole fraction. So what this really shows us is that the vapor pressures produced by distillation of a mixture of these two components, they're going to be dependent on each component's vapor pressure and their quantity, also known as the mole fraction. And so what we'll see here is that the total vapor pressure of the solution will be equal to or be within one of the extremes of the pure vapor pressure from cyclohexane and the vapor pressure from pure toluene. And that's because if you have 100% cyclohexane, which would be given by a 1.0 mole fraction for cyclohexane and a 0.0% mole fraction for toluene, then the vapor pressure of this, in that case, it wouldn't be a solution, it would be a pure compound, but you get the total vapor pressure would be equal to just the vapor pressure of cyclohexane because it's pure. So same thing with toluene. If it was pure toluene, we would just be looking at the vapor pressure of pure toluene. But because these are multiplied by their mole fractions, in reality, likely the vapor pressure produced will be somewhere in between the two vapor pressures of pure cyclohexane and toluene, which would be the two extremes. And then Dalton's law by itself will describe the vapor pressure produced by an immiscible multi-component system. Because when the two compounds like limonene and water don't mix, they each component will act independently of the other and exert its own vapor pressure independent of the other compounds present and independent of the molar fraction. Basically, what that's trying to say is because the two liquids don't mix, they each form their own system sort of independent of whether or not they're both there or there's only one there. So what we can use is just Dalton's law without thinking about mole fraction, because the mole fraction doesn't matter when the liquids are immiscible and forming their own system. And so what we see then is the total pressure when you have these mixture of these two immiscible liquids is just going to be equal to the pressure that's provided by limonene. And again, I'm talking about vapor pressure and the pure vapor pressure produced by water. So what we'll see then is that the vapor pressure, the total vapor pressure will be higher than the vapor pressure of just limonene or just water, because both components are there producing a vapor pressure and they're additive. So then the next thing that we really need to think about is how does the vapor pressure and the boiling point, what is the relationship between vapor pressure and boiling point? So this graph shows you that we have different organic compounds such as methyl chloride, butane, neopentane, and some others down here. And what we can see is that it's a graph of vapor pressure versus temperature. And you can see that the compounds that have the higher vapor pressure also correspond to the lowest temperature at their boiling point. This is the normal boiling point at normal atmospheric pressure. And you can see that methyl chloride has the lowest boiling point, the lowest temperature associated with its boiling point. and it also has the highest vapor pressure. What that shows us is that there's an inverse relationship between vapor pressure and boiling point. And in general, as vapor pressure of a compound goes up, its boiling point goes down. And that makes sense. If it's easier for the molecules to vaporize and become a gas, then the vapor pressure that we will that it will produce will be greater, and therefore it doesn't need as much energy to boil, since it more easily gets into a gas phase, and therefore it will correspond to a lower temperature or boiling point. So now that we know of that reciprocal relationship between vapor pressure and boiling point, we can go back to these equations that we were looking at. Remember, for the mixture of cyclohexane and toluene, which we'll be trying to distill using fractional and simple distillations, we saw that the total vapor pressure of the solution would be equal to or within the extremes of the pure vapor pressure of just plain cyclohexane or toluene separately. And then because of the reciprocal relationship, that means that the temperature will also be equal to or within one of the extremes of the boiling point of cyclohexane or toluene. So what we'll see is that the vapor pressure from toluene, since it's higher the vapor pressure of cyclohexane is higher than toluene because it has a lower boiling point. So the vapor pressure of the mixture will be in between the expected vapor pressure of the two components if they're pure, and the boiling point will also be in between those two extremes, meaning the boiling point of cyclohexane on the low end and the boiling point of toluene on the high end. So this is a graph that shows us a temperature on the y-axis and volume of distillate. We're going to be producing a similar graph in the lab, but we're actually going to just use time, and because we have no way of accurately measuring the volume of distillate over, in small quantities. So in order to produce the best graph, we'll just use time on the x-axis for the distillation. And so ideally, fractional distillations will separate the components better than a simple distillation. And to fully understand why, we're going to talk about the theory, but we haven't gotten to that yet. So what would happen for the graph in terms of an ideal situation is we would have a period of time where we're just collecting pure cyclohexane. So let's say about 15 milliliters or so of pure cyclohexane gets collected. And then all of a sudden, as the amount of cyclohexane goes down considerably, the temperature starts to go up and it would rise rapidly to the boiling point of pure toluene. This would mean we were able to collect pure cyclohexane. There's a very short period of time where there might be a mixture, and then we're able to collect pure toluene. And that would, of course, be a perfect ideal separation. And simple distillation is much more likely to produce a graph where it goes up more gradually instead of sharply, meaning we don't really ever collect pure cyclohexane. It's always some sort of mixture of cyclohexane and toluene, where it's more cyclohexane to begin with, and then later on, as that's removed, we eventually get fractions that are more primarily toluene. Okay, and then I wanted to say, but I forgot to, about the boiling point being between the two extremes of the boiling point of cyclohexane, which is about, I think it's about 82 or 83 degrees Celsius, and then toluene, which is about 111 or so degrees Celsius. When I say that the boiling point will be between those two extremes for the entire distillation, that assumes what's known as a minimum deviation from Raoult's law, which is basically this equation up here, which talks about how vapor pressure is lessened in proportion to its mole fraction. It's possible for this not to hold up with all mixtures of solutions, and more significant deviations of certain mixtures of liquids can occur due to intermolecular forces changing when you have a solution of certain liquids compared to other solutions of liquids. And sometimes if there's large deviations in intermolecular forces when you make a solution compared to pure samples of the two liquids separately, that could lead to a phenomenon called azeotrops. And that will be further explored in Chem 233. And that is not the case with cyclohexane and toluene. So what we talked about here will hold true for those two because they have similar enough intermolecular forces, because the structure is fairly similar, both being hydrocarbons. Okay, so let's move on to the steam distillation and see how the relationship between vapor pressure and boiling point will play out when we're talking about the total vapor pressure of a mixture of immiscible liquids. So what we saw is that because the two vapor pressures are additive and that the vapor pressure is not going to be dependent on mole fraction with immiscible liquids, that the vapor pressure produced by the mixture will always be higher than the vapor pressure of both components separately, which means that the temperature and the boiling point of the mixture will be lower than, I thought I had changed this to lower than the boiling point of, not the vapor pressure, excuse me, lower than the boiling point of limonene and water. So limonene boils at 176 degrees Celsius and water boils at 100. But what we'll see is that the mixture actually boils below 100 degrees Celsius. So it boils below both components' boiling points individually, which is really helpful because if we had to heat limonene all the way up to 176 degrees Celsius, at that temperature, things can happen like decomposition of molecules, and so that's not ideal. So it's better if we can find a way to boil it at a lower temperature, which is why we take advantage of the vapor pressure produced from water. So because water has the lower boiling point compared to limonene, its vapor pressure will be quite large at any given temperature. For example, at 99 degrees Celsius, the vapor pressure of water is 733 milligrams of mercury. As a result, limonene will distill in spite of its low vapor pressure, because it will only need a vapor pressure of 27 millimeters of mercury at 99 degrees Celsius to distill. And that's because we need to reach 760 milligrams of mercury, which is atmospheric pressure, for boiling to occur. And at 99 degrees Celsius, water is producing the majority of the vapor and the majority of the pressure and from that vapor. And so limonene doesn't have to produce as much in order to reach that threshold where we can get boiling. So it's very neat, but limonene will actually distill just below 100 degrees Celsius using steam distillation as a technique, which is great because it will not decompose at that temperature. Okay, so let's talk about the experiment, right? So for part A and B, we've got this miscible mixture of pretty volatile organic liquids. We have cyclohexane, boiling point of 81, and toluene's boiling point is 111 degrees Celsius. So you can see those temperatures are pretty close, right? 30 degrees apart means that a simple distillation is unlikely to be effective at separating those two components. And so we're going to be comparing fractional distillation and simple distillation in terms of its ability to separate these two liquids. So the way that we're going to do that is by doing the fractional distillation first. And then we're going to duplicate the fraction volumes that we collected in the fractional distillation on the second day using a simple distillation. So we're going to essentially collect the same number of fractions and the same fraction volume. And then we're going to submit samples for gas chromatographic analysis so that we know exactly how much cyclohexane and toluene is in each fraction. And ideally, of course, we would like to see that the two liquids are more efficiently separated using fractional distillation by looking at the GC data, because that would match the theory of how it's supposed to occur. And specifically, what I want you to look at is the composition of the mixture in the first fraction. Is it more enriched in cyclohexane? Meaning if you're comparing the very first fraction from the fractional distillation and the simple distillation, is there a greater amount of cyclohexane in the fractional distillation versus the simple distillation? If that's the case, then you can say that fractional distillation was able to more efficiently separate the mixture than simple distillation. So here's a picture of the setup of a fractional distillation versus a simple distillation. And you can see that the difference is primarily in the round bottom flask and its connection to the Claisen adapter. In the fractional distillation, we have a fractionating column in between those two pieces of glassware. And in the simple distillation, that fractionating column is just omitted in the setup. And so that's the difference, right, where we're hopefully going to use this fractionating column to help the separation of those two liquids. And again, you'll understand that more in terms of how that works as I delve more into the theory of fractional distillation. Okay, for now, I just want you to kind of understand the setup, right? So we're going to use a ring stand with multiple clamps. It's really important that you clamp the fractionating column if applicable, and also you want to clamp the round bottom flask. And then we use these Keck clamps, which are the yellow clamps that you see here, to make sure that there's a nice, the two pieces of glassware are properly joined. Because what we're going to do is when we actually start the heating process and the distillation, we're going to cover all of this glassware with foil. So it's not going to be easy to look at the glassware as the distillation is occurring. If you keep opening up the foil, you're going to lower the temperature of the glassware, and that will make it harder for the distillation to occur. So it's really important that you're sure that all of these ground glass joints are connected properly, because if there's a leak, meaning there's a disconnect and you don't know that it's there because it's covered by foil, then you could be essentially heating your mixture and then just losing it to the atmosphere, which is not what we want to happen. And then we're going to be using these LabQuests to monitor the temperature of the vapor right before it moves to the condenser. And that's just a little bit more data than we can, get using a regular thermometer. Using a regular thermometer, we would have to manually record the temperature constantly, which would be a lot of work. Now we can just digitally record the temperature as a function of time during the distillation, and then produce those graphs of the fractional versus simple distillation temperature versus time using the LabQuest, which is great. And so we have the, we're heating, right, the liquid mixture in here, and then over time it will migrate its way up the fractionating column. Notice the condenser. Notice that the water is going in on the bottom and then coming out and going into the drain on the top. If you have the water going in through the top and out through the bottom, it won't completely fill up the jacket on the condenser. And then we have another adapter and a round bottom flask that we're collecting into. and an ice water bath just to make sure that the liquid stays cool and isn't too hot, because we don't want the cyclohexane to evaporate after the distillation has taken place. And a nice jack and to hold it up there so that you don't have to manually hold it, works really well. And then a little variac that controls the temperature supplied to the heating mantle. Okay, so now I want to take a deeper dive into what's happening at the molecular level in order to explain the theory behind why fractional distillations are necessary to separate mixtures of miscible liquids with similar boiling points. So let's start at the very beginning, where we're looking at a pure liquid. So all of these dots are colored blue because it's meant to be the same molecules. So in a pure liquid, some of the more energetic molecules have enough energy to overcome the intermolecular attractions between molecules in the liquid phase and escape from the surface to form a vapor, forming what's known as a vapor pressure. The smaller the intermolecular forces, or the attractions between the molecules, the more molecules will be able to escape at any given temperature. You can see that they're showing 4 molecules currently escaping. And so as the temperature increases, the number of molecules having enough energy to overcome the intermolecular attractions and escape from the surface to form a vapor increases. And thus the vapor pressure increases. So I would have done for this picture maybe a few more, right? If we're heating it up, maybe a few more molecules have enough energy. And so more molecules are escaping, forming a higher vapor pressure. If you have a second pure liquid, the same thing is true. At any particular temperature, a certain proportion of the molecules will have enough energy to leave the surface and form that vapor pressure. It might not be the same proportion of molecules, but in this simple explanation, we're showing, again, 4 molecules escaping. So about the same, probably intermolecular forces or attractions, and therefore about the same number of molecules escaping. So now let's think about, what if we mix these 2 liquids, right? What's going to happen in terms of the vapor pressure above the liquid? So in an ideal mixture of these 2 liquids, the tendency of the 2 different sorts of molecules to escape is unchanged. So basically what that's saying is that the intermolecular forces between the 2 blue molecules and 2 red molecules are about the same as the attraction between a blue and a red molecule. And therefore the tendency to escape the liquid phase is unchanged. So we still have the same vapor pressure. This diagram is for about a 50-50 mixture of the 2 liquids. That means there are only about half as many of each sort of molecule on the surface as in the pure liquids. So if the proportion of each escaping stays the same, only half as many will escape in any given time. So what they're talking about is the composition of the surface, right, that's exposed to the air. And they're saying if you make a 50-50 mixture, about 50% of the surface molecules will be blue molecules and 50% will be the other component with the given depiction of the red molecule. And so if you have about 50% molecules at the surface, then about 50% of those molecules, or the same proportion of those molecules, but halved, would be forming the vapor pressure above the liquid. So if the blue molecules still have the same tendency to escape as before, that must mean that the intermolecular forces between the 2 blue molecules must be exactly the same as the intermolecular forces between a blue and a red molecule. If the forces were any different, the tendency to escape would change, right? So that's what they're talking about when they talk about an ideal mixture. The tendency to escape is the same because the intermolecular forces between the different molecules in a solution is the same as if they were still in their pure form. So of course, that's not likely to be the true situation with most mixtures of liquids. But that is, what would be the ideal sort of easiest to analyze situation. So exactly the same thing is true of the forces between two red molecules and the forces between a blue and red. They must also be the same, otherwise the red ones would have a different tendency to escape than before. If you follow the logic of this through, the intermolecular attractions between two blue molecules, two red molecules, or a blue and a red molecule must be exactly the same if the mixture is to be ideal. So, of course, no liquid mixture is perfectly ideal. Mixtures like cyclohexane and toluene, however, do get close to ideal behavior. Why is it very unlikely for them to be perfectly ideal? Because it's very unlikely that the intermolecular forces between two different molecules will be the exact same in strength from two molecules that are the exact same structure. And so it's much more likely, in fact, that you will get deviations from this ideal behavior, and that the intermolecular forces, in fact, will be a little weaker than they would be with their just as a pure liquid. And that's because the structures are different, so their ability to attract each other is going to be a little different. So in this graph, the vapor pressure of two miscible liquids are plotted against the mole fraction of each component in the mixture. The higher vapor pressure results in a lower boiling point. So B is the component with the lower boiling point, in this case cyclohexane, and A is the component with the higher boiling point, in this case, or in our case, toluene. So basically this is a graph where we have two y axes, and we have the vapor pressure of pure cyclohexane. And we know that this one is cyclohexane because cyclohexane's boiling point is lower than toluene, so its vapor pressure will be higher than toluene. And then we have on the x-axis the mole fraction, where we're going from 100% B all the way to over here, we would have 100% A, and then everything in between. So Raoult's law basically allows us to draw this straight line between the vapor pressure of pure A and the vapor pressure of pure B. Because it says that the vapor pressure of a mixture is going to be of a mixture of two compounds making up a solution, the individual vapor pressures of the two liquids will be proportional to their mole fraction, and that the vapor pressure of the mixture will be in between the two extremes of the vapor pressure of A on the low extreme and the vapor pressure of B on the higher extreme. And that if it's proportional to its mole fraction directly, then that generates a straight line, right? So basically, if you had a 50-50 mixture of A and B, you'd be right in the middle here on the x-axis, and you would expect a vapor pressure 50, basically exactly in the middle of pure A and pure B. Now, what is the actual vapor pressure above mixtures with these different compositions of mole fraction? Well, actual vapor pressure is a little bit higher. And that's because it's very likely, like I talked about in terms of the intermolecular forces, that the two components, it's very likely that they'll have lower attractions to a different molecule that's not the same as it is than another molecule. And so that actually relates to a greater tendency of the molecules being able to get into the gas phase, producing a vapor pressure, right? Lower intermolecular forces will lead to a higher actual vapor pressure. So while cyclohexane and toluene are not ideal, meaning that intermolecular forces between the two molecules are not as strong as in the pure samples of them, it's close enough that it's essentially works the same as being ideal in terms of the ability to separate them using a distillation. So the actual vapor pressure of a mixture of miscible liquids differs from the ideal vapor pressure because the intermolecular forces holding A and B are usually weaker than A to A or B to B. The weaker intermolecular forces leads to a higher vapor pressure. But we do want to notice here that the highest vapor pressure anywhere in the graph here is the vapor pressure of pure B. In cases like this, where the deviation in terms of actual versus ideal vapor pressure is small, they behave just like ideal mixtures as far as distillation is concerned. Specifically, if the highest vapor pressure is pure B, then that means that will correspond to the lowest boiling point, and it will be possible to potentially separate pure B in the distillation. So let's convert the vapor pressure graph to a boiling point composition diagram. We'll start with the boiling points of pure A and B. B has the higher vapor pressure. Remember that we said this is cyclohexane, this is toluene. And so B having cyclohexane having the higher vapor pressure means that it will have the lower boiling point. So this is now the boiling point of pure cyclohexane and the boiling point of pure toluene. Remember that this is 81 degrees Celsius and this is 111 degrees Celsius. So again, because vapor pressure and boiling point are reciprocally correlated, then we're still, basically we just switch higher vapor pressure to lower boiling point. All right, for mixtures of A and B, specifically miscible mixtures, that's what we're talking about here when we use fractional distillation. You might perhaps have expected that their boiling points would form a straight line, joining the 2 points we've already got. Not so. In fact, it turned out to be a curve, again, because the actual vapor pressure is not ideal. They're talking about this blue line here, right? If you take a 50-50 mixture, is the boiling point of that mixture going to be exactly 50 or halfway between the boiling point of cyclohexane and toluene? So if the difference was 30 degrees, then let's say 15 degrees higher or lower than the two components. So that would be about 96 degrees. You might expect, sorry. You might expect a 50-50 mixture of those two liquids to boil at 96 degrees, halfway between the two individual boiling points, but that's actually not the case. It will boil a little bit lower than expected, again, because the vapor pressure above the mixture of the two is actually higher because of decreased intermolecular forces. So if you were making this graph, it would be important to take great care when drawing this curve. The boiling point of B is the lowest boiling point because the vapor pressure of pure B is the highest overall vapor pressure. So don't let your curve droop below this. Basically, it means when you're drawing this blue line, don't go too extreme with it and go below in terms of the y-axis and the boiling point of pure B. That can happen with certain mixtures that deviate quite a bit from ideal, and it has consequences that will be explored in Chem 233L, where we're talking before about the azeotrophs. Okay, in order to make this diagram really useful, we're going to add another line. This second line will show the composition of vapor over the top of any particular boiling liquid or liquid mixture. Okay, so the basis behind this is that if you have a mixture of two miscible liquids and you heat it up and it starts to boil, is the composition of the vapor going to be exactly the same as the composition of the liquid? The answer is no. And if it was the exact same all the time, there would be no way to separate them. But in fact, the vapor composition will be enriched in the lower boiling component, meaning the one that has the lower boiling point, well, more of those molecules will escape into the gas phase. And so the gas above the liquid will be enriched in the compound with the lower boiling point. So if you boil a liquid mixture, you will expect to find that the more volatile substance, i.e. the one with the lower boiling point, escapes to form a vapor more easily than the less volatile one. That means that in the case we've been talking about, you would expect to find a higher proportion of B, or cyclohexane, in the vapor than in the liquid. And so that is why we end up with these two lines, because vapor composition is not going to be equal to liquid composition at any given temperature. Okay, so what this diagram is showing us is that we're going to be heating up a mixture. Let's say it corresponds to whatever this mole fraction would be, right? Maybe about 80% A and 20% B. So we're heating up this mixture of 80% A and 20% B. And eventually it's going to boil at a given temperature, right? We're going to call that the boiling point, and that's measured on the y-axis. And then if we look at the vapor above the liquid at this temperature, it will be more enriched in A. And so that vapor above the liquid will actually have a composition that has more B now, because it's the more volatile component, and less A. So how would we know exactly, right, how to make that pink line? Like, how do you know exactly how to draw it or where it corresponds to? Well, that actually can be generated experimentally. Because if you boil a liquid mixture, so you can boil different mixtures of cyclohexane and toluene, you can find out the temperature at which different mixtures of those two liquids boil. And then you can also measure the composition of the vapor over the boiling liquid, because if you condense it, the composition of the vapor is exactly equal to the composition of what has boiled over, what you've condensed, the condensate that you've collected. So then you'll be able to measure, right, the composition of the vapor above the liquid, and you'll be able to eventually create a line here, right, by measuring various different liquid compositions and then noting the composition of the liquid and the composition of the vapor as it boils at any given temperature. So a bunch of data points here. Vapor composition will allow you to generate the second line corresponding to the vapor composition. So successive vaporization condensation cycles are called theoretical plates. So basically what this is showing us is, you can see this light blue line, that's one theoretical plate. This red line is another theoretical plate. And a third line is green box here. And so what is that corresponding to? So let's say that you take a mixture of two components at composition 1 and you heat it up, right? Eventually it will boil at a temperature, and we can plot that on the y-axis. And then we can collect the vapor above the liquid by condensing it. And if you take the vapor above the liquid and condense it and collect it, it will have composition 2, which will be more enriched in the lower boiling component. So let's say you take the condensate that you got from that first distillation and you put it through another distillation cycle, another simple distillation, where you heat it up, allow it to get to its boiling point, condense the vapor above the liquid, find out that it's at composition 3 now, even more enriched in the lower boiling component. And then you do that again. So you take the condensate and resubject it to another simple distillation. You get the idea. Eventually, you're going to be pretty close to pure B or pure, whatever the lower boiling component is. In our case, it would be cyclohexane. So you could do successive simple distillations and eventually lead to pure cyclohexane. But that would be a very time-consuming process. And so we want that essentially to happen all in one distillation, as opposed to a series of different distillations. Okay, so how do we get that to happen all in one distillation? We do what's called a fractional distillation, which includes a fractionating column. And that column will either be, in a simple case, you could use a condenser that has some glass spikes on the inside to be able to hold beads inside of it. Or you could use a fractionating column, which is also known as a Vigoro column, which basically they've produced these glass intrusions into the inside, which creates more surface area for multiple theoretical plates to occur before you've even collected any condensate. And remember, a theoretical plate is a vaporization condensation cycle. Okay, so let's go ahead and read what it has here, make sure I've explained everything well enough. So you can see that we now have a vapor which is getting close to pure B. So after 3 vaporization condensation cycles, also known as theoretical plates, we're starting to get pretty close to pure B. So if you keep on collecting the condensate and purifying it, re-distilling it, eventually you will get pure B. That is the basis for fractional distillation. However, doing it by a series of simple distillations would be extremely tedious. Real fractionating columns automate the condensing and reboiling process. And the way that works is by having boiling stones or glass, a special glass column, right, where there's a lot of surface area of glass inside of the column. And that provides a surface for the vapor to condense and then re-vaporize and condense further up. And eventually it's gone through multiple theoretical plates, but all inside this piece of glass, as opposed to collecting it and resubmitting it for another distillation. So the vapor condenses on the increased surface area. The condensed vapor is enriched in the lower boiling component. And then that liquid is then reboiled. So instead of basically condensing back in the original round bottom flask, it condenses in the column and then is re-vaporized multiple times to go through multiple vaporization condensation cycles. And therefore, we hopefully would get much more pure compound B or cyclohexane coming out of the end of just one distillation. So let's relate what's actually happening in the fractionating column to the phase diagram. So suppose you boil a mixture with composition C1. Right? So we're coming up here, we're boiling at a certain temperature. The vapor over top of the boiling liquid will be more enriched in the more volatile component, and we'll have composition C2, right? So that vapor starts traveling up the column. Eventually, it will reach a height in the column where the temperature is low enough that it will condense to reform a liquid. So in a fractionating column, it will condense on the glass surface area inside of the fractionating column. But if that wasn't there, then it would just recondense and drip back into the round bottom flask, which would mean that it remixes and it doesn't actually have a chance to condense in a composition that's more enriched in the lower boiling component. So what happens to that liquid, right, that it's now started to condense inside the column? It will start to trickle down the column because it's a liquid, right? So gravity will push it down. And where it will meet new hot vapor that's rising up the column. This will cause the already condensed vapor inside the column to reboil. So some of the liquid at composition C2 will boil and now give a vapor with composition C3 that we can collect higher up the column. And if that happens enough times, right, if the column is large enough where we have multiple vaporization condensation cycles occurring, then the ideal situation is hopefully we get to pure B coming out of the column initially, followed by later on, once that is removed, then we would start to have pure A come out of the column. So the idea would be if we take C2, a composition C2, and we heat it up, right, and we collect the vapor that we condense, and it has composition C3, and so then that's removed, right, from the original mixture. Now the new mixture is not the same as C2 because we've removed some liquid with composition C3, which is more enriched in the lower boiling component B, or cyclohexane. So basically, if you end up condensing a liquid that has more cyclohexane in it than toluene, then when you are reheating the leftover liquid, it will have more toluene in it than cyclohexane proportionally compared to the original mixture, because you've removed some proportionally more of the cyclohexane than the toluene. You start off after that with a mixture that would be slightly to the right on this x-axis scale, more enriched in the higher boiling component toluene. So when you do this vaporization condensation cycle, if you only do one theoretical plate, you would get a composition that has slightly more toluene in it than to begin with. So basically that means as you remove cyclohexane from the mixture, the leftover solution will be more and more enriched in toluene. And so eventually you're going to be collecting fractions that have more and more toluene. And that kind of makes sense, right? Because the cyclohexane has disproportionately been removed from the solution. Okay, so that was the end of the pre-lab lecture on the theory behind distillation and introduction to the experiment. Hopefully between this and your Joe videos on fractional and simple and steam distillation, you will feel like you understand what's happening in the experiment and feel ready to come in and try it yourself. I hope you guys have a wonderful day.